Okay, so let's try to write equations for slope and equilibrium for this problem. So as we talked about in class, we're going to have to write two moment equations. One that's good from 0 to L over 2, and the second one from L over 2 to L. And then integrate those moments to find slope, integrate them again to find displacements, and then take care of our integration constants by matching things that we know. And then we'll talk about how the two equations have to match here in the center. So I don't think we need to go into all the details. I think you can see from this problem, since it's a simple supported beam and the load is in the middle, that my reactions are going to be P over 2 on both sides. Okay? So now if I want to write an equation for moment that's valid between 0 and L over 2, then my free body diagram would look something like this. I have my reaction of P over 2, and at some distance x, I'm looking for my internal moment. So all I have to do is sum my moments about the cut, make sure it's in equilibrium. So what's the moment, the sign of this internal moment here? Is that positive or negative? Positive. And then the moment caused by P over 2 is negative. So it'll be P over 2x. So you can easily see the moment's pretty simple. It's just Px over 2. Not so bad, right? Right. So let's go over here now and do from L over 2 to L. So when I cut the structure here, I think it's more convenient to look at the right-hand side. So in this case, I'll draw my free body diagram. And there's my reaction, P over 2. Oops. I have my internal positive moment, M. Now remember, the distance to the cut is x, so the actual length of the segment is L minus x. So now when I sum the moments about the cut of this side, make it in equilibrium. The internal moment is negative, using right-hand rule, and I have a positive moment generated by P over 2 times the distance L minus x. So again, the moment's not too bad. The moment is simply P over 2 times L minus x. So not a very challenging problem to find the moment equations. So now what do we do with it? We integrate. So let's go back to the first section and recall that the slope of that section is the integral of m over EI integrated along the length of the beam. So in our case, looking at our equation, we've got a P over 2 as a constant. So I'll pull all that out and I'll get P over 2 EI, and I just have the integral of x dx. Not too challenging. So that ends up being P over 2 EI, and this is what? X squared over 2. Oh, almost forgot. Plus a constant. So there's my equation for slope. Now at this point, do I know anything about the slope in this part of the beam? Do I know it at the support, at the pin support? No, I don't know what the slope's going to be. Now, since this beam is simply supported and there's a point load just at the center, it is possible to know that the slope at L over 2 is 0. But for right, you can use that to your advantage. Of course, if this load is just shifted anywhere from the center, that won't be true. So let's just not do that right now and see how we can get it on our own. So right now I can't do anything with this. What I can do next, though, is I can go and integrate the slope and get the displacement equation. So I'll integrate this thing. So again, I have P over 2EI, and then now I'll have x cubed over 6 plus C1x plus C2. So now I've got an equation for slope. Now, what do I know anything? I said slope, but I have an equation for displacement. So what do I know about displacement between 0 and L over 2? We do know the displacement at the pin support. It's 0. So I can here go, hey, the displacement at x equals 0 is 0. So I plug that in, 0, 0. What does that say? C2 is 0. So I can go ahead and cross that out. That one's gone. Let me use a different color. Maybe it'll show up better. Great. That's the beginning, right? Now let's go over here. I'll try to split the paper in half so you can kind of keep track of it. Let's go over here and look at the right-hand side. So again, let me go and do this. Let me go back and call this 1, Roman numeral 1, to indicate that's from this section, and I'll put this as section 2. So now my slope in section 2 is going to be the integral of the moment in that section divided by EI, which in our case, here's the moment in 2. So again, it looks like we're going to have P over 2EI as a constant. And I have the integral of this. So that'll be Lx minus x squared over 2 plus a constant C3. Do I know anything about the slope in the second half? Well, as I mentioned before, we could use the idea that the slope at L over 2 is 0. And that would make this problem slightly easier to solve. But in general, you don't always have that condition. So let's just leave it alone right now and see if we can find it another way. So now I'll do the displacement at 2. What is that? Well, that's the integral of the slope. So I'm going to integrate this. So I'll still have P over 2EI. When I integrate this, I get Lx squared over 2 minus x cubed over 6 plus C3x plus C4. So, oops, I keep bumping the page. Sorry about that. So there's my 2 equations for slope and displacement. Hey, I know something about that for sure. I know that the displacement at B is 0. So I know that the slope when x is equal to L is 0. So now I have to evaluate this at x equal L. That's a little more challenging than the other side. So when I do that, this is a constant, so I don't have to worry about it. So looking at the first term, I have L cubed over 2 minus L cubed over 6 plus C3L. Oh no, plus C4. That's a bummer. One equation, 2 unknowns. Not good. So already we seem to be stymied. We're not done yet. What else do we know? Well, this is the new thing I want to talk to you about. When the equation for slope from section 1 matches section 2 at this point here, can they change value? Can your slope suddenly change value at a point? No, it could if your material actually bent, but our beam's not going to bend about a point. So what that tells us is that the slope from equation 1 at x equal L over 2 has to equal the slope from equation 2 at x equal L over 2. You see that? Continuity of slope. They can't change value. Maybe the one you can see more clearly is the displacement. So if I use my equations from section 1 and evaluate them at x equal L over 2, it should be the same as the displacement from equation 2 at x equal L over 2. Why is that? Well, whenever I come down here and find a displacement, it suddenly can't change between the two. That means the beam is broken. Again, that's not something we allow. So what I've ended up doing here is I have one constraint. I now have a second constraint. So this would be my third and fourth constraint.
So you can only do it at that one point.
Well, that's the only point the two equations share.
Right. Okay.
Now, if you look at what you'd have to do to solve it this way, let's just look at that quickly. So if you look at the first equation here, theta 1 and theta 2. Well, theta 1 has what? C1 in it. Theta 2 has C3 in it. So that'll just get you a relationship between C1 and C2, or C3. The displacement equation, well, this one doesn't have any constants, but this has 3 and 4. You see that? Oh, I'm looking at the wrong one. This one has 3 and 4. And then, of course, your previous one also has 3 and 4. So now you have two equations in 3 and 4.
Yeah.
But you have to solve them simultaneously. So that becomes a challenge. Now, if I gave you this for homework, and you had lots of time as a resource, you could probably finish it. What's the likelihood of me requiring you to do this in an exam where I'm expecting you to pull it off in 15 minutes?
0.
A unanimous response of no way, Jose. Or in other language, 0 probability. So this is for your, get ready for it, education.
Thank you.
You're welcome. Now, this problem could be solved simply, this problem alone, in that we know when this beam does displace, that right here, the slope is so we could use that to our advantage and actually find the solution to this problem quicker. But in general, if I move this load off center one way or the other, that condition is not true. It's only 0 slope at the maximum displacement, and we just happen to know the maximum displacement's in the center. Again, if I move that, L over 3, 2L over 3, doesn't work. You'd have to go this way. But you can still do it, given enough time. And of course, these equations will look a whole lot nicer if you know P is a number. If I gave you values for all that, and L is a number. So these equations would be all numerical instead of these symbolic equations. You guys probably know from your experience in 2107 using MATLAB that MATLAB will do symbolic algebra, and you could put these equations in MATLAB and say solve it and done. Maybe I should assign this problem to you and ask you to do it in MATLAB. That's a great idea, Mr. Fisher. That's exactly what I'm going to do. I'm going to assign this problem for the next homework and require you to solve it using MATLAB.
Well, wait, when I took MATLAB, it was just visualizations. I never learned MATLAB.
What did you have? What did you have in MATLAB? What did you have for visualization? No, this is computational.
Computations.
What did you have? What language?
We had MATLAB. MATLAB was new last semester.
Oh, it was just last semester. Okay. Well, I'll have to withdraw that. Although it'd be really cool to have that experience. I think you would appreciate. It'd be for your education. All right. Any other questions before I stop this? All right.
That's it.
That's it.